and acceptable. So you can kind of tell that there's a peak here in G2. We see the slow degrade of blood leaving. In G3, we see multiple peaks, and we're unclear whether the true peak from the actual pulse is there. So we're not quite sure if, let's say, the first peak is the correct one or the second one. So this would be an example of an unfit or a poor signal quality, because we're not able to say, you know, this is the true peak from the blood source. This is actually from noise.
And this is you're saying that this unfit noise can be caused by a number of factors, right? It can be like whether you're running or whether you're, I do have an Apple Watch, sorry. I needed to say that. Or whether you're like, it's too loose. It's like all of these things can cause that, right?
Yeah, poor, so if it's not fit properly, if you like sweat a lot, if you have tattoos, if a lot of hair, like there's a whole range of things that can cause the signal quality to be poor. But things that we can tackle is really noise, like in terms of, you know, improper fit, that is going to be something that is kind of outside the control. But in terms of noise, we can control, we can at least try to attempt to control that. Good question. Okay, so when we had this idea of, okay, we want to use wearable devices and tackle AF estimation, we knew that noise was going to be a problem. And so we really decided to kind of start this research project from the ground up. It's important to note that, you know, medical data sets are quite limited in terms of what's available publicly. And this is mostly because it takes a lot of time to be able to consent patients, find correct patients. We have to pay attention to patient privacy, and also these types of studies tend to be very expensive, not only monetarily, but time-wise. So there was really a limitation on what publicly was available for me to use. And so we decided to create our own data set in-house, and we partnered with Samsung to be able to address our aim, which was to create a method to classify atrial fibrillation episodes in wearable devices. We did this in 4 different ways. We wanted to evaluate the use of convolutional denoising autoencoders. We did this also through using the benefits of simulated data. We incorporated joint learning and multitask learning for signal quality and rhythm estimation. And then we also ran an external prospective validation study. So I'm going to talk about each 4 of these points now. So I highlighted earlier that, you know, noise is a problem. So what can we do methodologically to address this? And so this is kind of where I did a lot of work in the audio realm, because these types of signals are very similar to some of the speech signals that you would get. So, you know, what do others do? That's kind of, you don't want to reinvent the wheel. So you want to see, you know, what's available to you and how can you be creative to your use case or your task that you're given. So we first wanted to address of how can we clean up the signal in terms of get it to a point where we felt it was in a good signal quality state, so that we would have our best shot at saying, you know, this is AF versus a regular, normal, healthy signal. So we wanted to leverage convolutional denoising autoencoders. And so what that does is that it essentially is a deep learning method that the input is a noisy signal in our case. It has an encoder and a decoder, and then the goal is to recapitulate the signal with the removal of that noise. And so in an ideal world, you would have both the clean signal and the corrupted signal. In our case, the data that we were pulling off the patients is only going to be this corrupted signal. In some cases, the corrupted signal may have a higher amount of noise than others, but we don't actually know the true underlying clean signal. So we weren't really able to use the data that we collected from individuals. So we use simulated data to do this, because in a simulated situation, I know exactly what that true underlying signal here is, right here denoted on the right, and I can add varying amounts of noise in different types of ways to then train those types of convolutional denoising autoencoder to get the signal as clean as possible. Okay, and so it's important to note that, we can't do this with real signals and that we really needed to leverage simulation data sets. And so I spent a large amount of time creating a novel simulated data set that would mimic real individuals. So here's an example of some of the simulation work where we have here on the top row, as we move down the rows, we have an introduction of more noise. Here's a really simple example where I just added various amounts of Gaussian noise. So that it gets to the point where on this bottom row, that true underlying signal, you can't even say, this is where that true peak was as we move along the signal length. And the reason why we did this is, again, we want to be able to handle various amounts of noise. It's really tough to estimate, what true level of signals out there in the real world, but in a simulated way, we can simulate tons of different types of noise artifacts and hopefully have the best set of noise simulations to be able to train off of. Okay, so once we had our large set of simulated data, we trained our convolutional denoising autoencoder that you see here. So here is an example, a very simple example on the bottom, where we see in black right here on the left is an observed PPG signal that's pulled from a patient. And we do see kind of high frequency noise throughout. So we can probably detect the true peaks, but once we ran it through our convolutional denoising autoencoder, we do see kind of that clean signal that we're hoping for. So this gave us kind of faith that this type of approach would work quite well in terms of being able to address the noise situation here. It's important to also say, what if it's not working? So what type of sensitivity analysis can we do to test whether or not the denoising is working properly? So we don't want a situation to happen where the convolutional denoising autoencoder introduces a physiological signal where there is actually no true physiological signal present. So here what we did was I just generated random Gaussian noise. And we don't want to throw this random noise into our trained model and then it produce these wonderful peaks and valleys that look like true signal when actually it's not there, because that would be quite dangerous. And so what I did was I generated random signals, and I wanted to say, if I use a general smoothing filter and the output of our convolutional denoising autoencoders, how similar are those? Because essentially what I'm really hoping happens is that our convolutional denoising autoencoder acts as a smoothing filter, where it smooths out most of that underlying noise, and it's not introducing these huge artifacts. And so we found here that we didn't see any introduction of, fake or physiological signals. And so we had very high faith that it wasn't going to introduce these fake signals if they weren't present here.
But these type of examples were not part of the training. So like you didn't do kind of, I know you wouldn't, sorry?
We didn't do random noise, is that what you're saying?
Yeah, so like during training, the model never saw random noise going as input, right?
No, we did. So during training, we go back here. The data set was quite massive, where we essentially had very clean looking signals, so very easy examples, to ones that were completely different. And then we also introduced completely random signals as well. And then those weren't changed between input and output. So in that situation, a small percentage is it kind of exactly like this, but a majority is not. Okay, so here is going to be a breakdown of our demographics for our study. So we were able to collect around 107 individuals from Stanford Hospital that underwent a cardioversion. Essentially, that is where patients come in and they are in a persistent state of AF, meaning that their AF has gotten to a point where they have to undergo a situation where they go under anesthesia and they kind of get that electric shock to hopefully restart their heart in normal sinus rhythm. So we consented 107. I also consented an additional 41 where they were going under stress tests at the different types of cardiovascular tests, but these individuals have other cardiovascular issues besides AF. And then we pulled an additional 12 people from the only publicly available data set that was available at the time. So the whole point of this is we try to include as much publicly available data set. Let me think of the AF would be our target, and then we also included the 41, which would be other cardiovascular issues, but that are not directly AF. So again, my collected data and then my public data is right there denoted. So this is where we wanted to, when we started building the algorithm, we first just tried to create a classifier that only classified normal versus AF. But we really found quite quickly that the incorporation of two correlated tasks, such as signal quality and AF, really helped and benefited our model quite greatly. So here's an example of how we did this. So we had expert reviewers look at different lengths of signal and grade them on whether or not they were excellent, acceptable, and poor. And these are signals that come directly off of the device. They haven't gone through my convolutional denoising autoencoder whatsoever. We made sure that that hand-graded data set included both the sinus rhythm, so normal rhythm, and atrial fibrillation. And here are going to be the results of when we look at the correlated task of only signal quality, how well we're able to classify between excellent, acceptable, and poor. I do want to note that the acceptable here in orange or yellow is going to be the one that's performing probably the worst out of the three that we looked at. And it kind of makes intuitive sense. This is going to be the range that some reviewers aren't quite sure about. They know that it's not excellent. They know that it's not poor, but it's not excellent. So it's in that middle ground. So it makes sense that our model is doing, it also is kind of fumbling on those windows as well. So it makes intuitive sense that the results that we were getting were mimicking the human choices that the training data consisted of. So recall that we used essentially the convolutional denoising autoencoder to clean up our signal. We wanted to use kind of those learned trained weights as a good basis for training. So we extracted only the encoder region of our trained convolutional denoising autoencoder and transferred that over to our model that would both consider signal quality and rhythm classification. And the reason why we wanted to only use the encoder part of our convolutional denoising autoencoder was because we know that that's part of the model that takes the input and essentially condenses or compress that signal to an area that's going to be so compact that it has all the information needed to recapitulate it. So this would allow us to get to a small, essentially a small representation to then be able to branch and focus more on. So here you're going to see on the bottom is going to be our deep learning method, where we ended up going through a couple of rounds of hyperparameter tuning in terms of adding additional layers and then focusing on the branching that would focus on either the signal quality or the rhythm classification. Our input into this is going to be 25-second lengths. That's ultimately what we highlighted in the paper. But we did look at various lengths of monitoring as well, which I can talk about towards the end.